I think I'm through the first wave of technical glitches anyway. So what we're going to talk, how did milestone 1 go actually? Let me ask that first. Did it go fine? Looks good, okay. Everybody seems pretty confident. Okay, so on to milestone 2. And I know, you've got reading week coming up, so you're like, well, what can I do during reading week? Well, you could get started on milestone 2. It's actually not a bad idea. So you've got quite a while to do milestone 2, but it is going to get busy towards the end of it because you're going to have a written document, milestone 2, and then oral presentation. Milestone 2 is more open-ended than milestone 1, so there's probably more to get going to get a baseline solution, and then there's kind of no end to it, which means if you're having fun, you can keep going. You can also stop. We don't expect you to just keep working on it all the time. But over reading week, if you get started, that would be a good idea. And what we're going to talk about today, you haven't had a lecture on this yet, so you have a lecture on Thursday as well that goes over, kind of gives an overview of milestone 2. This is going to jump right into a walkthrough of how do you start attacking it. So ask me questions if certain things aren't clear, and some more background will be given in the lecture on Thursday. Okay, so how do we attack milestone 2? So what do? How many people have read the handout already? Okay, 1, thank you. We spent a lot of time writing this. I want to see somebody read it. I'm going to give you bonus marks. But it does help, right? In one part of the handout says, well, how do I get started? So we're going to follow those instructions to get started right now. Milestone 2 is about graphics. How many of you have written graphics before? Okay, so then you wouldn't have at U of T. So you've written some graphics before, or were you just stretching? So yeah, okay, so you wrote some HTML. Was it interactive or not? Yeah, okay, so you've written some, but most people won't have written graphics, which is fine. So you're going to learn how to write graphics in milestone 2. I find graphics very fun. It's part of why it's like in this course, so hopefully you'll enjoy it. Okay, so there are layers in graphics. I'll talk about that in the lecture on Thursday, but in brief, there's a graphics library that we're using called GTK. It's what most of the applications on the Linux machines that you're using in the lab are written in. GTK is huge, okay, and it's a bit daunting at first. Like to just get a window open takes you quite a bit of code. And it provides relatively low-level functionality for things like visualization. So to make it easier, we've written a layer above that called ece2. So ece2 basically layers on top of GTK. It's easier to get stuff set up. It provides some additional functionality that is helpful for what you're going to do where you're visualizing stuff. But if you want, you can also go underneath it and directly call GTK. You don't have to, but you can. So those are kind of the layers. In this tutorial today, we're just going to use ece2, and you can complete all of milestone 2 only using ece2. But you do have to understand how it works. So read the quick start guide. It's not that long, and it has an example program. That example program is probably the best way to learn how ece2 works. It's a form of documentation, right? You fire it up, you see what is it doing to draw this stuff. So you go, okay, I kind of now know how to do those things. Okay, so yeah.
Sorry, before you begin with the milestone, I had a question about milestone mentioned some extra features, and there is a grading rubric for the TA.
Yeah.
So in that grading rubric, there are like difficulties, and based on that, there are marks. But in the end, it also writes that there are some extra marks from 0.5 to 4 according to difficulty. So are all those extra features, or like the ones whose difficulties are mentioned are extra, but there is a mark accordingly, and the extra features are marked by the TA?
Those are all possible extra features you could do. Maybe I'll pop this up just so people can see what the rubric is like. And I probably shouldn't be showing you my emails. I don't know what that email was, but let's see. So let's just open up a window here, and that's a fairly harmless one. That's Alex and I making sure we have the code working for the tutorial. So you can see that there's teamwork everywhere. Okay, so let me go to Quarkus. Actually, Quarkus does not like Chrome on my computer, so let's do this. So we'll go to Quarkus. And I'm going to bring up the rubric. Okay, so there's the instructions. You should read those on your own time. Here's the grading rubric. and you should definitely read this. Okay, so the grading rubric is, you have some basic features you have to implement. You have to be able to visualize pretty much everything in a city that's in the kind of higher level API we gave you, the Streets Database API. You want it to be kind of usable, fast, responsive. And then there's this milestone is worth 16 marks. 5 marks are for extra features, things that we didn't tell you you had to do, but show us something interesting. And then there's 2 marks for code style and project management and wiki. Okay, so for those extra features, we give you some ideas. You can do anything you want. If you're wondering, like, is this a good extra feature, a bad extra feature, you can talk to your TA. Don't start working on extra features, my advice, until you get all the basic ones going. But this is part of why it's not a bad idea to start in a reading week, because there's a reasonable amount of stuff you can do. We've given you some hints though, right? Some of the students are, well, what might I do as an extra feature? So this shows a bunch of possible things, like maybe I just have a mode where I can change the color scheme. It's really easy, so it's only worth a maximum of half a mark. And you want to have this add up to at least 5, right? Because there are 5 marks for extra features. If what you do adds up to less than 5, it's obviously impossible if we get to full marks. Changing the color scheme is pretty easy, right? That's why it's only worth 0.5. There are some other things that are more difficult. For example, showing bus routes, right? So you have to go into the OSM data, the lower level API, extract that, figure out how to draw it. So that's worth 2 marks. And getting a bunch of data off the web, like live traffic updates and stuff, is a reasonable amount of work, so that's worth 4. Does that make sense? This is if you do it well. So, this is like, it's like a maximum. If you basically go, well, I tried to get live traffic data, it doesn't really work, but I draw a little car icon here, your TA is not going to go, you get 4 marks. You know what I mean? They're going to assess, okay, you tried something difficult, it doesn't work very well, I'll try to figure out what to do here. Does that make sense? If you try more extra features, which you're free to do, we'll grade, your TA will grade kind of the best ones. Like, we'll look at them all, but we're not going to do a thing of like, hey, I did enough extra features that it adds up to 10. I did them all badly, right? So you should only give me 50% on each one, but that's still 5. No, your TA will pick like the ones that were best executed to give you the best shot at getting to 5. Does that make sense?
And from your previous experience, what's like the aim for the extra features that we should go for?
So we give you this so that you basically have like sort of an endpoint. You don't have to write like 50 extra features. I mean, you can if you wish and you have the time, but you don't have to, because your TA is going to go, I'm tired. That's lots, great. You know what I mean? So you should pick extra features from this or make up your own that add up to at least 5. If they add up to somewhat more than that, it gives you a bit of a margin of your, a couple of your TA doesn't think we're done well. Maybe you could just say, okay, well, let me look at this other one. Does that make sense? For outstanding implementations, your TA can also give bonus marks. Okay, so there's not a hard cap on this, but that will have to be quite good. Does that make sense? Okay, so good question. Let me go back to the slides here. Okay, so you've got some background reading to do, and I really strongly encourage you to do that background reading. Let's see if I can find let's hide this. Okay, in this milestone, you do have a main program. Okay, so there's a main.cpp because your TA, you are actually going to demo. The way this is graded is you're going to demo to your TA in about 3.5 weeks, and actually a little longer. You're going to be done in 3.5 weeks, but then you're going to demo to your TA the week after. So, and you're going to demo your mapper program. So you are going to have a main.cpp. It's going to be pretty simple. It just launches your code. Most of your code is still going to be in libstreet map source. And then the main thing you're doing is you're writing visualization of the map. So you have to start writing a function that can draw the map. This is where, and it obviously have lots of helper functions. We're not actually suggesting you write everything in that one thing, but you're going to have a main control routine that can draw a map, and it's going to do all sorts of other stuff. That's where you spend most of your work. Okay, so main function. So we give you a skeleton main function. So you run ece297 and ece2. It's going to put some extra files into your project. Okay, and it's going to put a skeleton. Well, you already have a skeleton main.cpp file. And your main.cpp should look like this. Basically, the one we give you, you load a map, we draw a map, and then you close a map. Okay, so your main should look similar to this, right? You can add extra features if you want. Why I'm showing you this is that draw map function does not load the map, it does not close the map. We also have some unit tests that can just help you see lots of different maps that run val grind. So you can also run ece297 exercise. Your TA is not going to run that, okay? But you can run it to see different maps. The way ece297 exercise works is like this. It calls load map, says draw map, then it calls close map. If you make your main program work the same way, it's just going to make life easier for you because the unit tests will work and your main program will work. Does that make sense? There's not going to be all that much code in main.cpp, right? Just kind of gets your graphics, calls the routine, loads the map, calls the routine to get the graphics going. So the style or the overall flow is going to be, you call load map, you call this draw map function, which will execute for a long time. It's going to actually interact with the user, let them look at the map, etc. And then there'll be a close map call to close up. So, you could put this in a helper function, like what I've shown here doesn't have to be in like the main function, but this is the style. What we call draw map is expects that a map's already loaded, and after it's done, it expects the map to be closed. Does that make sense? And that's so that we can still unit test it. That's the way ece297 exercise is going to call it. So this is the only function, that it has to have that name. So you've got one new function you're going to write that has this name so that the unit test can test it. Okay? Is everybody with me on that? Okay. Okay, so first thing I'm going to do, so agile development, right? We're going to just try to get something working. So first goal is just to create an empty window. And in graphics, creating an empty window is harder than just doing a printf. But ece2gl makes it reasonably easy, okay? Because it's doing a lot of work behind the scenes to get stuff set up for you. Okay, so this is what we want. We want to basically just get an empty window on the screen. And ece2gl, if you read the quick start guide, you'll see that it automatically creates some buttons for you. So you don't have to, once you get ece2gl running, you're automatically going to get these buttons. They'll let you kind of do panning and zooming. So that's going to be taken care of for you. Okay, so how do we do that? Well, we've given you a header file, just like we had m1.h. There's a header file we wrote called m2.h. You can't change it, it's read-only. m2.h is really simple though. All it does is it says there's a function called draw map, okay? And that should draw your map, and it should assume the map's already been loaded. So that's all that header file says. Make this one function and our unit test will now work. So I need to include that header file. I also need to include these two header files. So we've already put, when you run ec297 and init2, we actually put source code into your project. And that source code is all in a subdirectory under libstreetmap source called ece2gl. And that is this higher level graphics library that we've written for you. Yeah?
Does the map get drawn on an application or a website?
It's on an application, right? So it's not going to a website. It's basically direct drawing on your screen. Does that make sense? So yeah, there are two header files, and sometimes people in C++ call header files .hpp instead of .h. Okay, my TA who did some of the work on this basically like that, so that's why it says .hpp. But there are two key header files you got to include. Application.hpp, this is basically control code to get things started and to create what are called widgets. Widgets are things like buttons that you can click on and interact with. And graphics.hpp. And graphics.hpp is basically for drawing primitives, like lines, polygons, changing their color, etc. You're going to need both these things, right? You need to get a window going, you want some buttons so people can tell you things, but this is a visualization program. So you're going to draw a lot of lines and polygons and so on to visualize a city. These two header files are all you need to include to get that. Okay, so draw map is supposed to bring up the graphics. So here's my draw map function. And what I do is I first say, I basically am declaring in the ece2gl namespace, okay, so ece2gl, we've made basically a library. Well, it's a namespace, which is all the functions that we've written for this graphics layer. And so that they never get confused with anything else, they're all in a namespace called ece2gl, just like std is a namespace. So I'm saying in the ece2gl namespace, there's a class called application, And in that class application, there is another class, another type called settings. Okay, so that's what I've asked for. And I just made an object called settings. And now settings is basically a struct, right? Like I can just directly access some of its member variables. It's got a member variable called main UI resource. And this is all well commented, so you'll see this in the code. Okay, a UI resource is something that's not code, but it's important for user interface for drawing. So this main UI resource is basically the window layout. It's like, where should the initial buttons be? How should this window look? Okay, we've already made one for you, and we put it in your project. It's called main.ui. I'm going to show you after reading week how you can change it. So if you don't like the look of the UI, I'm going to show you how you can go changes, but you don't have to. Just leave the buttons where we put them, and you never have to edit this file. So that's UI layout. There are a couple other things. So what is the name, the string name of the overall kind of top level main window that we're creating? And we've called it main window in this main.ui. And a canvas is something you can draw. Okay, so buttons are like things you can click on, and the graphics library will kind of keep track for you. The canvas is like draw anything I want on it, right? I draw lines, polygons, etc. So we're drawing cities, we need a canvas somewhere. And that's where most of your work's going to be to visualize this city. It has a name of main canvas. And now what I'm doing is I'm calling the constructor for the ece297 application, and I pass it this settings object. You can just take these lines as boilerplate and just go, I'm copying them, right? Because we've set up a UI layout. You tell basically ece297, here's the UI layout, and that's it. So there's no need for you to kind of go change these. You can leave them alone. Okay, so this is going to construct this application. And then this function here, we're calling a member function of the ece297 application called run. It takes 4 parameters. They're all what are called function pointers. Does anybody know what a function pointer is? Okay, so a function pointer is you're actually passing, here is a function that I want you to call when something happens. Okay, so we are telling, and right now I'm saying, don't do anything when stuff happens. I'm going to pass you 4 null pointers, which means I don't want you to interact as much at all. Okay, so I'm going to show you what you can do later. But right now, the simplest way to get this window going is we're going to call the run method, which is going to run for a long time. Okay, it's not going to come back. It's going to interact with the user, redraw, get mouse clicks, all sorts of stuff. And as I said, it takes some optional parameters to basically call your functions when certain things happen, but we're saying don't call me. I'm just gonna, those are null pointers because I don't want you to do that yet. We're keeping it simple. Okay, so I kind of told you all these things. Yeah, so this is different than other functions you've written because this function is not going to return for a long time. It actually won't return until a person clicks on a button I'm going to show you, or basically closes down that window. So this could be running for days if you want. Okay, and what is this going to look like? It's going to look like this. It's going to bring up a window that has nothing very interesting in it, except these buttons that ece297 makes automatically. And these are basically panning, buttons to move your display around, buttons to zoom in and out. And this proceed button is special. It basically says, I'm done, return from this run routine, go back to the rest of the program. Or if I don't like doing that, I can also hit the X button, right? Either of those is going to close this window and it'll go back to continue on in your program. Does that make sense? Okay, so let me demo that. Okay, so bring this up and okay, that should start. We'll see what happens here. I don't know why that hasn't started yet. But I can do this without Visual Studio Code too. Kind of annoying. That is strange. That makes me think code is, let's see. I'm gonna see if I can make this, kill this. That was strange. Okay, so, all right, I made you this whole thing from the command line today then, which is fine. Because I think what happened, VS Code, like basically you saw like the machine I was logged into went crazy. I think VS Code is still somewhere running on it and it won't open right now in this project. So in the break, I'll try to kill it, but I'll just use like a text editor to show you what's going on. This is why it's always good to know how to use a text editor, because you never know what's going to happen. Okay, so let me show you this. Okay, so I've got this function called drawMap2. It's kind of a helper function. And right now, all it does, let me go back there. Okay, so this function is going to get called. It's like my draw map, okay? And I have this draw map minimal function, which basically does what I just showed you. Okay, it's going to create an empty window. It's like the simplest, just get me an ece297 window open. And so I'm going to compile this and run it. That's weird. Okay, hopefully that is not going to be a big issue. All right, so I'm just typing make. When you build in VS Code or an IDE, it's just calling make behind the scenes. And the program I want to run is called Mapper. And I made it so that by default, well, right now it doesn't do anything very interesting. So it basically did exactly what I showed you. It creates this window. I can click on the buttons. Actually, this one I didn't even hook the buttons up to anything, so I can't even click on the buttons. But I did successfully open up a window, but I can't do anything. You know, click on the buttons, it's like false. But it's still progress. I did something. Okay, so let me keep going here. Look at this. I'm filling rules. Okay. Okay, so we've got a window open, but we can't really, it doesn't draw anything, and if I actually click on the buttons, they crash. So that's not great. I gotta do better than this. So what do I want to do? The next thing I need to do, if I want to draw something, is I have to define a coordinate system. So in a lot of graphics libraries, including GTK, the coordinate system is pixel-based. Okay, so you actually have to work out how big the screen is, and you have to draw this pixel and that pixel. It's actually a real pain. You move your program to a bigger screen and it works differently, and you usually wind up with all sorts of coordinate conversions all over your program, because you don't actually, you'd have to be trying to work out, well, how big is Toronto in pixels? And you wind up with code all over the place doing that. So one of the things ece2gl does for you is it lets you specify whatever coordinate system you want. And behind the scenes, it will translate all the calls you make to draw stuff into pixels. Okay, but it's kind of now abstracted from you. You don't have to worry about pixels. So we can ask for any coordinate system we want. And what I'm doing here let's see if I can find my mouse cursor, is, well, I guess I don't even need a mouse. This initial world, I've defined, okay, so we've got another type in ece2gl called a rectangle. So you see everything that ece2gl, you go ece2gl namespace, colon, and then what is it? So I'm asking for a rectangle, and I'm creating an object of type rectangle, calling it initial world, and I'm giving it 2 coordinates. These are actually XY points. So I'm saying 0, 0 to 1000, 1000. Okay, so what is this? Well, if you look inside those header files that I showed you, you'll find this is basically the 2 corners of my coordinate system. Okay, so my X low, Y low is 0, 0. My X high, Y high is 1000, 1000. That's my coordinate system that I want to draw. Okay, so I've created that initial world. And now I basically, remember, application is the name that I gave to the ece2gl object. And I basically am calling a method in it called add canvas. Okay, this method is an important one. It's basically going to hook up the area where I can draw my city, okay, where I can draw lines and so on. I'm going to call it main canvas. That name's important. It has to match what we put in the UI layout, so just leave it at that name. And so this basically lets ece2gl figure out, what are you talking about? Like, where do you want to do this drawing? So don't change this name unless you're going to change the UI layout. And then I give it this coordinate system. Okay, so that's the coordinate system I'd like to use to draw. So 0, 0, like to 1000, 1000 should correspond to that whole drawing area. And you now know what I mean when I start drawing in a certain spot. And then this last thing, draw main canvas, is actually the name of a function. Okay. And that name could be anything I want, but I have to write this function. So I said it's going to be called draw main canvas. I now need to go write that function. What this function does is it draws whatever I want to be on, in that main drawing area. Okay, so in our case, we want it to be a city. So this should be a function that can draw a city. It's going to be big when you do a real function, so you should have many, many helper functions, right? Do not write like some 700 line monstrosity, but the name of the overall, the entry point, the main function, I have said will be draw main canvas. Okay, so you probably haven't seen things like this before. I guess I'll show you, and then, well, maybe I'll hold off on that till I show you the next line. And then I basically tell ece2gl to take control again. So I call application.run, which is going to hand control the ece2gl. It's going to start drawing. Create the window, draw it. Does it make sense? Is everybody with me? Okay, so so I basically told ece2gl that when it wants to redraw that canvas, the main drawing area, it has to call this function draw main canvas. Okay, so I need to write it. So I already said it'll be called draw main canvas, so I know its name. If you look in the header files and the documentation for ece2gl, it tells you what this function must look like. It tells you its signature. It takes exactly one argument, and that one argument is a pointer to an ece2gl renderer. This is another ece2gl object. So this is an object that basically lets you get at the drawing calls, right? For drawing primitives like lines and rectangles and polygons. And you can't change the signature. ece2gl is going to be calling your function, and it is going to be passing you a renderer. If you basically did not make this function signature, it will not work, okay? It won't compile, and it wouldn't work if it did. Okay, so in this function, I have this renderer, we just called it G, and the way you access all the primitive drawing calls, like drawing rectangles and lines and so on in ece2gl, is through the renderer object. So I'm basically saying call the method of the renderer called draw rectangle. If you go look at the header file comments, it's very heavily commented. It says, well, that takes, again, 2 points that form a rectangle. So I'm basically saying, well, I want a rectangle from 0, 0, x equals 0, y equals 0, to x equals 1000, y equals 1000. Does that make sense? If you look inside the graphics.hpp file, you'll see there are a whole bunch of different things you can draw, but they're all documented. You can go look at them. So let's go look at what do you think this is going to draw? So given my coordinate system, how big do you think this rectangle is going to be? It's going to be small? Is it going to fill most of the screen? What do you think? So I said the coordinate system was 0, 0 to 1000, 1000. What do you think? Yeah, it's going to basically fill the whole window. So my drawing calls and my coordinate system should match. Okay, so this is what we expect to get. All right, so we get the window we had before. It has buttons and so on, but we're going to draw a rectangle. Okay, and we can make other calls in ece2gl to say how thick this rectangle should be. So I've asked for it to be thick, so it's going to be a thick rectangle. Let me show you this, and then I'll ask you a couple of questions about it. Okay, so we go back here. All right, so let's look at the code again. So let's look at that text editor. But I guess the code is what I just showed you. So, but okay, so basically, I'm gonna comment out what I had before. I'm gonna change to the code I just saw you on the screen. That's a little more complicated. All right, so this is the code I showed you. This should look very familiar. And here I called my screen redrawing function draw main canvas blank. Let's go see what it looks like. Okay, so here's that. Okay, so it has a couple more lines than I showed you. It's setting the color to black. So it set color, I'm setting a red, green, blue into this, and I want it to be black. I set the line width to be 10 units. Okay, these actually are pixels. So basically I set the line width to be 10, and so it's gonna draw it thick. And then I draw the rectangle where I said I would. Okay, so let's do a make on this. We're the wrong one. So let's go over here and do a make. Okay, and I run my mapper again. And it does what I said, right? So I can take this window, I can make it bigger. I can zoom out, and this rectangle gets smaller and smaller. I can zoom in, it gets bigger again. I can also, this is a touchpad, I can use pinching to zoom in and out too. And I can grab the screen by clicking left, drag things around, etc. Okay? So I didn't write very much code to do that. Like you saw, my redraw function is actually 3 lines long. It says draw a thick rectangle in black. So what's happening, ece2gl behind the scenes, as you zoom in and out and so on, it's reinterpreting how much of your coordinate system is on screen. Okay, this is one of the advantages of drawing in what we're calling world coordinates. So the reason that we call the coordinate system like initial world is world coordinates in graphics means the coordinates that kind of are natural to you. Okay, so I'm drawing in world coordinates, and inside ece2gl has something called a transformation matrix, which basically it knows how zoomed in and out you are, and it knows what your coordinate system is, and it's converting all the drawing calls you send to it into pixels. So even though I'm drawing, basically when I click zoom out, what will happen is ece2gl will call my redraw function, okay? But my redraw function, because ece2gl knows I've zoomed out, it's changed this transformation matrix and my graphics map differently to the screen. So I didn't change anything, but I already have pan and zoom and redraw. Well, pan and zoom and so on. Does that make sense? ece2gl will redraw, like let's say I hide this window. Okay, so maybe I'll bring this in front of it. Okay, so it's gone. Now I'll shrink this down, it comes back. The way that happened is ece2gl knows the window's been revealed, it has to be redrawn. It knows how to redraw the buttons, so it'll do that automatically, but the main canvas where you're gonna draw your city, it doesn't know how to draw that, it just calls your redraw function. Okay, so your redraw function gets recalled whenever it's necessary to redraw the screen, and it has to redraw the screen. That's why it's not segfaulting anymore. The reason the very first one segfaulted is ece2gl actually called my screen redraw function, and I didn't write it, so it crashed. So now I have one, it doesn't crash. This rectangle is not quite filling the whole screen though. It's filling much of this white area. This white area is the main canvas. It's where I can draw. But it's not filling it all. Why do you think it's not filling it all? is this window square? No, it's not square. So what ece297 did is I asked for a coordinate system from 0, 0 to 1,000, 1,000, but the window area is not square and it doesn't want to distort my graphics, so it basically expanded things a bit. It said, well, you asked for, from x equals 0 to x equals 1,000, but I'm actually going to need from x equals maybe negative 400 to x equals positive 1,400, so that I don't distort things. You got some extra screen real estate. If I made this white area perfectly square, then it will fill the whole thing. Okay, because now I don't have any extra coordinates visible on either side. Everybody with me? Okay, so let's go on to the next thing. We're going to gradually build this up. Okay, so let me hide these controls again. Okay, so I just did that. Okay, so now we want to do something a little more interesting than drawing a rectangle. We're supposed to draw a city. So I'm going to start drawing a city. You don't actually have to draw intersections if you don't want to. You have to draw all the streets, but the intersections if you want, you can draw the little dots where the intersections are. If you think that's ugly, you don't have to. But I'm going to draw intersections because they're a little easier to draw than streets. So in order to organize my code, I'm going to make a little struct called intersection data. Intersection data has two things. It has the position, the latitude and longitude of an intersection, and it's got the name of the intersection. Okay, so in my draw map function, I'm going to, I'm basically gonna, I make another global variable. Okay, so I make a global variable called intersections. So that's what I've chosen to do. And at the very start of this draw map function, I'm going to write some code to just load up this global variable intersections. It has this data that I want to get at in order to draw it. Okay, and then after I'm done that, I'm going to call this application run just like before to hand control the ece297. So this is not a hard question, okay? And I'm to encourage participation. If you guide me through this, you can draw this art. Remember any functions that I should use to get this data? Or what's the basic structure for me to load this up? Yeah. Yeah, so I can say get num intersections and write a for loop. I'll go through for every single one and I'll basically say, give me the position of this intersection, right? So there are functions like that in the streets database. So if I can grab a chocolate bar if you want, break, you can do it if you like. So it's exactly what you said. Okay, so I'm going to get the number of intersections. I'm going to make my vector. I'm using a vector to store this data, so I'm going to make it size the number of intersections. And I'm just going to go through, and for every single intersection in the city, I'm going to basically store its position, and I'm going to store its name. Okay? I don't even have to do it if I didn't want to. Whenever I need this data, I could just call the streets database API. I've decided I'll store it in this vector because it makes the examples a little simpler and it may make the code a little faster. Okay, so I've got this intersection data now. What am I going to do with it? Well, I'm going to make a smarter redraw function, right? My redraw function was just drawing a rectangle there. That is not going to get me many marks in this milestone. So I want to draw intersections instead. I'm going to keep my rectangle, okay? But now I want to draw something else. Okay, so anybody else wants to try for a chocolate bar in the break? Like, how are you going to write your code to draw every one of these intersections? This is the basic idea. And don't worry if you don't know the exact function names and so on. Just tell me roughly what you do. What do you do? Yeah, so you've got this big vector of intersections. Just going to loop through it. Yeah. 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 So this is a really good answer. Okay, so you're like 3 demos ahead. So you're saying get the lat, convert to XY, then draw them all in the for loop, right? By making some call, we got this renderer, right? So this always is passed to a redraw function. So you can call something like maybe draw circle, or in ece297, a filled circle is called fill circle. So we call that. So that will work well. Good idea. I'm not as smart as you, so my code's not quite as good as yours. But it's the same idea. Okay, so basically what am I doing? Size t is just another name for unsigned integer, so don't be annoyed by that. So I'm basically going through all the intersections, and for every one of them, I've already stored their position. So I'm gonna call the x equal, I'm just gonna set my x coordinate is equal to the longitude. My y coordinate is equal to the latitude, which I've already stored inside of these intersection vector. And then I don't want magic numbers. So I'll say the width is 10 and the height is 10. And I'll say, I'm not going to draw circles, I'm going to draw rectangles. But basically, from that renderer, we can call it has another member function. It's got a whole bunch of member functions that are documented in the header files. It's got one called fill rectangle. I give it an x low, y low, and an x high, y high. So I'm just saying from the latitude, longitude, the longitude, comma, latitude, to those values plus 10, draw me a rectangle, okay, between those two corners. Everybody with me? Okay, so let's go look at how that works. So I'm going to, pretty sure I have a demo of this too, so let me demo it. Okay, so this is the code I just showed you, right? I guess I didn't show all of this, but basically I'm loading up that intersections vector. I'm setting up the window again like I did before. I call application run. And let's see, what is this? One thing you'll notice is I tell it my redraw function. Okay, so I always need to do this add canvas. It's always going to be main canvas unless you actually go change the UI layout, but it's any function name you want. So I basically say it's main canvas XY, or draw main canvas XY, which I've written up here. And that is the code we just talked about. Okay, so we're saying we're going to draw it in black, we're going to draw a big rectangle, and then we're going to draw all the intersections. Okay, so let me build that. See if I need the other window for that. Okay, so make to build it, type mapper to run it, and doesn't look much different than what I had before. Okay, see the big rectangle? Where are all my intersections? It sounds like 190,000 or so intersections, 200,000 intersections. Where are they? Just see this rectangle. Does anybody know where'd they go? Yeah, what do you think? Yeah, they could be out of bounds. Maybe they're just right off the screen. In this case, they're actually on the screen, but see this black dot here? That's Toronto, okay? It's not the most inspiring representation, right? It's not clear you can go find your house or navigate very well. So how much do latitudes and longitudes change in Toronto? What is the latitude and longitude of Toronto? Anybody know? I know, actually. So, okay, what's the latitude? Let's know that at least. Like, it's between 0 and 90. So we're not at the North Pole, we're not at the equator. So what do you think it is? Does anybody know what latitude we're at? Okay, so we're above latitude 43. Okay, it turns out that our longitude is around 43. Okay, or 44. So how much do you think when you go from one street to another, your latitude or longitude has changed? How far apart are lines of latitude? What do you think? So you think very little, right? Yeah. So from one street to another, like a couple hundred meters, your longitude and latitude are not changing much. They're changing a little, but you have to go look down like 4 or 5 decimal places. The distance between the line of latitude is about 112 kilometers. Okay, so that's bigger than all of Toronto. So there's distance between the line and longitude varies. At the equator, it's 112 kilometers. At the North Pole, it's 0. But basically, they're big. So we just directly drew the latitude and longitude, and we drew them all size 10. right? 10 units. Doesn't really make sense. They all wind up in one tiny spot because we just made up this coordinate system. We just said from 0, 0 to 1,000, 1,000. But that's not really an appropriate coordinate system for latitude and longitude. Does that make sense? So we kind of, you look at it and you kind of go, it seems totally wrong, but it is what we asked for. Yeah. So some of what you're going to do in milestone 2 is debugging things like this, where you expected something very different than what you got. Okay, so let me go back and let's try to fix this. Yeah, so this shows. Let's hide these controls again. Yeah, so that black dot is where all of our intersections are. How are we going to fix this? So what do you think? There's 2 ways to fix it. One way is horrific and one way is easy. So let's see if you come up with the horrific or the easy way. So I'm going to come to you in a second and see if anybody else wants to get in on this question action. Even if you get the horrific one, I'm going to give you, you come up on the break and get a chocolate bar. What do you think?
Maybe scoping it down to that, like a set of latitude and longitude and dividing intersections on the basis of latitude that they cover and like having their thickness according to that.
Yeah, okay, so you're going to try to change the thickness, like the size of the rectangle. Is that what you mean? So that's a good point. We need to think about like how big this rectangle should be. What about the fact that all my latitudes and longitudes are just one tiny spot? So changing the size of the rectangle can help me, maybe they're not all going to be on top of each other anymore, but they're all still going to be, just in this very small region of the string. So any other ideas? What do you think?
Maybe like just scoping the map down like that.
Yeah, so how would I scope the map down to that?
Maybe not drawing the rectangle from like 0 to 1,000, but like for only that much area.
Yeah, so basically, those are good answers. So you're basically saying change the coordinate system, right? So the right way to change this is you just say, this coordinate system makes no sense, right? Like I just made up 0, 0 to 1,000, 1,000. What I should do instead is find a more reasonable coordinate system that will fit Toronto in whatever units I want to draw in. Okay, so I want to draw in latitude and longitudes. I should try to set my coordinate system to basically bound what's the smallest latitude and the biggest latitude and the smallest longitude and the biggest longitude in Toronto. If I was to set that to be my coordinate system, then Toronto's going to fill the whole screen, and that makes more sense. Is everybody kind of with me? The other way, so that's a good way to do it, because EasyGL has, as I said, has this transformation matrix. You can ask for any coordinate system you want, and it'll take care of it all, right? And it'll take care of it as you zoom in and out and everything. The other way to do it, which is horrific, you should not do, is you just say 0, 0 to 1,000, 1,000. That's the way it is, and I'm going to start inside all my drawing calls trying to do all sorts of conversions myself. Don't do that, right? That's like really bad software engineering. The graphics library will do the conversions for you. Just ask for the right coordinate system. Does that make sense? Okay, so we're gonna basically yeah. So I guess this is the same what I said. So we're drawing this latitude and longitude, and the coordinate system we chose is just inappropriate for this. So we need to fix that. So how do I do that? So sometimes students ask, well, can we ask libstreet's database API, like what is the maximum latitude and the minimum latitude for a map? And you can't. Okay, we don't have that data. It's not in the OSM data. We don't give it to you. But you can figure it out yourself. Okay, you can just go through, for example, all the intersections, and you can figure out what's the biggest latitude, what's the smallest, etc. Where should I? Does that make sense? Anybody want to take a crack at this? Is not that hard, but how would you write the code to find the maximum latitude? So I guess I'll give you a big hint. There's a piece here, and then there's a loop. So let's just take maximum latitude. What should we set it to up here? Before we go into the loop that looks at all the intersections. What do you think? Yeah, so set it to a small number. Okay, so I can set a double min. That's a very good one. It's the smallest smallest double number you can have. So that makes perfect sense. Okay, I mean, there's another technique. If I could just set it equal to the first intersection's latitude, that'll work too, but your technique will also work perfectly fine. And so basically, and then for the minimum latitude, I want to do the opposite, right? Well, here I'm just going to set it equal to the first intersection again, but if I did your technique, what I'd do is set it to a really big one, right? And then I'm basically going to go through all of the intersections. And what are you going to do at every intersection now? Check this max and min, right? Like, is it, so basically, we're going to basically make the max lat equal to the maximum of what it is right now and the latitude of the intersection we're looking at. Okay, and we're going to do that for all the coordinates. So standard code to go find the maximum of a bunch of numbers, minimum of a bunch of numbers, etc. Where should I put this code, do you think? So I've got some new code. Where should I put it? Got a couple options. So my one option is I put it in my redraw function, right? I can put it there. Do you think I should put it in my redraw function? It's probably not the best place to do it. Like, first, I need to know it to set the coordinate system. So I need to have it before I ever call my redraw function. Also, I want the redraw function to be fast. The redraw function gets called a lot. So a better place to put this is in my load map. Put it in load map, and then I just store it. And now I can use it both when I'm setting the coordinate system, and I can use it when I'm redrawing, if that's helpful. Maybe I don't need it when I'm redrawing. If I do need anything like that, maybe it's useful to be able to get the max lat and min lat quickly. Okay, so I've got this. And basically, now that I've computed these max and min longitude and latitude, I can use that as my world coordinates. And then none of the rest of the code changes. Everybody with me? Make sense? Okay, so if you do that, this is what you get. And let's see if I have that on a demo. I don't think I did. I think consider this one. So this is actually what you will get, but I'm not going to demo it. Why do you think I got this? I correct my latitude and longitude. My little rectangle of black is now a big rectangle of black. What's wrong? Okay, so this is my drawing code. Okay, I haven't changed it. This is still what I'm doing in my redraw function. I did change the coordinates. Anything here to make you nervous? Yeah. Yeah, I'm drawing all the intersections. And how big am I drawing them? Like, what size is my rectangle? So this is the call to the draw rectangle or fill rectangle. And it's basically going from the latitude, longitude of the intersection to, add width and height. Width and height are 10. How big is that? It's huge, right? 10, like that's like 1,000 kilometers, right? Like 10 lines of latitude is like over 1,000 kilometers. So it's gigantic. So all my intersections are just on top of each other. I'm drawing them way too big, okay? So if I use like a one, if I do some experimentation, I'll find that like a 1/1000th of a line of latitude is more reasonable, and 1/1000th means about 112 meters. Okay, that's kind of, well, most intersections are probably like 112, maybe 200, 300 meters apart, so that seems more reasonable. Like now, maybe I'll get some separation between the intersections. So I draw with that, and hopefully this will look better. The question we get sometimes is like, well, should the width and height change based on the zoom level? If I always draw it the same width and height, then basically my intersections will get bigger as I zoom in. If I like that, I'm good. And usually I kind of like that. But if you decide, well, at a certain point, maybe I don't want them to get super big, well, then you'd have to write some more code. And there are more, we're going to talk about this in lecture, but there are functions you can use to figure out if you're really zoomed in. So if you want to change how you draw as you zoom in, you can. But if you don't change anything, what will happen is the intersections just look bigger. And mostly that's what you want, but maybe the details you'd like to change. Okay, so if you do that, you're going to get something that looks like this. It actually does start to look like droplet. Okay, so, and I'm going to go show you that to convince you that it exists. Okay, so let me bring up this really quickly. Okay, so it does look like what I said, and we're not doing anything special as we zoom in, so the intersections do get bigger. And mostly I think that looks good. So seems reasonable, but like I said, you can ask ece2 questions to figure out how zoomed in you are. If you decide when I'm really zoomed in, I prefer to draw things a bit smaller, you could do that if you want, okay? Okay, so it looks much better. Let's go back here. Let me hide this again. Does this look right though? Like, does this look? It's kind of like Toronto. Do you think there are any problems with this, or does it look perfectly correct? Let's remove this. Okay, so what do you think? How many people think this looks, correct? Okay, so mostly, anybody think it looks wrong? You think it looks wrong? How does it look wrong to you? So it seems like it's. So you think it looks kind of like Toronto, but distorted? Is that what you're saying? Yeah, and it is actually distorted. So this is. So if we look at map of Toronto, you'll find this looks a little bit too wide and fat. You know what I mean? Like it looks a bit distorted where it's been stretched out horizontally or pressed vertically. It's not totally wrong. It still kind of looks like Toronto, but it doesn't look perfect. Why do you think it looks a little bit distorted? It is a bit subtle, but the TAs know this. They actually will. They know. We tell them to watch for this. Okay, this is actually a common error. So don't do this. Why do you think it looks distorted? So it has to do with how I'm drawing it. What am I drawing? So I'm going through all the intersections. I'm drawing them as I'm getting their lat long, and I'm drawing the rectangle there. Okay, and I made my coordinate system lat long, so everything lines up. That's good. So does that result in any problems? What do you think? Okay, so how, again, let's go back to latitude and longitude, right? Latitude and longitude really come from like a spherical coordinate system. So lines of latitude are always 112 kilometers apart. The lines of longitude, it varies. At the equator, they're also 112 kilometers apart. At the North Pole and South Pole, it's like 0. They all converge. And in between, you have that function that was given you in the milestone 1 handout. It's basically the cosine of your latitude, right? It's 112 kilometers times the cosine of your latitude. That models the fact that as you're getting closer to the poles, all of the lines of longitude are convergent. We didn't do anything like that here. We just directly drew the lines of latitude and longitude. Toronto is at about 43 degrees. That means that a cosine of 43 degrees is about 0.7. Okay, so here a line of latitude is 112 kilometers apart, but a line of longitude is only about a little less than 80. But we drew them the same size on the screen. So what that means is that we kind of stretch things. We're drawing our lines of longitude too far apart because we're drawing them just as far apart as the lines of latitude, but they're actually only 70% as far apart. So we've kind of stretched the map horizontally by, 1/0.7. Does that make sense? So it doesn't look totally wrong, but it looks a bit wrong. And if in your map, if you go look at things like Spadina circle that are supposed to be circular and they look oval, get nervous, right? You go, wait a sec, did I do the right projection? So it's not quite right. How can we fix it? And I think we're now we're getting close to your solution that you proposed right at the beginning. What do you want to do to fix this? You do want to do a projection. So don't draw latitude and longitude directly. All map makers do projections. You're now a map maker, okay? So you use those formulas that are in milestone 1. And what you're doing is getting a projection into meters on the surface of the Earth, okay? And the projection will distort a little bit because the Earth is round. But in the local region, it's pretty accurate, okay? So that the distortion is somewhat unavoidable, right? Unless you make a curved screen like the surface of the Earth, you can't do any better. But within the region and bounds of the city, the distortion is very small. So use the milestone 1 projection equations. Okay, so those equations were basically take cosine of the average latitude, multiply by the longitude and the radius of the Earth, and you're going to get work. That'll give you the x coordinate of where you are on the surface of the Earth. Do something similar for the latitude, but with no cosine, you get where the y coordinate of where you are on the surface of the Earth. You don't want to write that code all over the place. So it's not a super complicated formula, but you're going to wind up converting various things. So don't write that code all over. You want to make a helper function. So what we've done is made a couple of helper functions. One that gets an x coordinate from a longitude and one that gets a y coordinate from a latitude. Notice that there's no, this requires also the average latitude, right, of the map. I didn't pass it in. What I'm doing instead, well, what do you think I did instead? Like, I need the lat average, but if I don't have that, I can't actually do this. I didn't pass it in, where did it come from? Yeah, it's global variable. I already have some global variables that basically load map works it out. Okay, so load map's going to store that, and I'm going to use that in this function. So I don't feel like passing it around all the time. What's the point? I could have done this with, maybe I could have passed the x and y together, and I could have gotten, or passed the lat and long together, and I could have gotten back the x and y together. That's also a reasonable thing to do. Maybe that's an even better helper function. So maybe you could write it, I'm not saying I'm showing you the best code style. That actually probably would be a slightly smarter helper function in my opinion. But at least do some helper functions. Don't scatter this all over your code. We're going to wind up with these conversions being used a lot. Also, the inverse can be useful. So I'm going to say, I'm going to go and invert the equations that are in milestone 1 using my amazing knowledge of algebra. And I'm going to write the functions that can get me a longitude from x coordinate and a latitude from y coordinate too. And I'm going to use those later on. Okay, now that I've got these helper functions, it's not too hard for me to use them. Basically, I say, I'm going to go in my redraw routine, I'm still going through all the intersections, but instead of directly drawing the latitude and longitude, I'm actually going to get that longitude and I'm going to call my conversion function to get an x. I'm going to get that latitude, call my conversion function to get a y. One of the nice things about these XY coordinates is that this is meters on the surface of the Earth. It's actually easy to understand. So I can actually say, well, how big should I draw an intersection? I'm going to say 100 wide and 100 tall. And I actually know what that means. It's like 100 meters. Seems reasonable, right? Like most intersections are around 100 or 200 meters apart, so it seems reasonable. Maybe it's too big. If I want it too big, maybe I'll make it 50. But it has kind of physical meaning. So it makes it easier for me to make the graphics work. And I'm going to call my old friend fill rectangle and just do that. Okay, so if I, okay, so I've changed my redraw function. This is my initialization routine, right? This is in my draw map function that gets the graphics up and sets the coordinate system. Is there anything I should change here? Okay, so redraw function I'm now happy with. It's drawing an x and y. Should I change anything here? And I'll give you a hint. I wouldn't show it to you if you didn't have to change something. So there's something I got to change here. What do you think? Yeah. Yeah, I got to convert these coordinates. So EasyGL makes it kind of easy to choose. You can choose any coordinate system you want, but you have to be consistent. Okay, so I basically changed my redraw routine to use these x and y projection coordinates. I can't tell EasyGL my coordinate system is still latitude and longitude. It makes no sense. My graphics will be somewhere way off the screen. I won't see anything. So I need to change these, and my helper functions make it easy. Okay, so I just call the appropriate helper functions to convert these coordinates. That's my new initial coordinate system. And if I do that, Toronto now looks normal. Okay, so it basically stretches out. And when you see them side by side, you can see the difference, right? Like one of those looks kind of like Toronto, but not as much. And let's see. So I'm going to do a quick demonstration of that, and then we'll take a break for a few minutes. And I will attempt to get VS Code working again. Okay, so hopefully that looks better. And yeah, it's still all interactive, still draws. Okay, so let's take a break until, I'm going a bit slow, maybe 5:28. And then I'll try to pick up the pace there. I want you to jump over, up here and grab one. So we going again? Okay, so we've corrected the projection. Let's see. Okay, so here's our code that has corrected the projection, right? We're computing x and y for every intersection. Okay, let's look inside these helper functions to see what we're doing. Okay, why do I want to look inside these? Because this drawing canvas is speed critical. Okay? Every single time that canvas needs to be redrawn, which means you zoom in a little, you click on your mouse and drag the picture around a little bit, that's called panning. All those things, they each require a redraw. So we want that to be fast, because otherwise your map doesn't feel very interactive. Okay, so let's look at what we're doing in here. So inside this is my x from long function. So inside my x from long function, I pass in a longitude, and it basically does this math. Okay, it takes the longitude, multiplies by a constant, multiplies it by another constant, multiplies it, well, it doesn't multiply here, converts my average latitude to degrees, and this average latitude I worked out in load map, so I stored that, and then I call cosine. So it's not a lot of work, okay? So it's like several multiplies. These are actually both constants. So when I turn on compiler optimizations, I build release, the compiler is smart enough to multiply those two constants together at compile time and store what the unified constant is. Okay, so actually one of these multiplies won't really happen. The compiler is smart enough to get rid of it. But I'll have one multiply, two multiplies, three multiplies, because they multiply here, and a cosine. Okay, so it's not a ton of work, but it could add something. I'm going to do a quick math test to see how fast you guys are, to see how much work something like this is. So I want how about this team? Do you guys want to compete against them? I'm going to give you each a math problem. We're going to see how, it's very simple math problem, see how fast you can answer. Okay, just because the computer has to do this, every redraw, it has to do this for about 200,000 intersections. Okay, so when the computer's fast, so it can do that, but we want to see, well, is this going to take any time at all? Maybe we can optimize this a little bit. Okay, so we can see which of you two is fast, which team is faster. So you guys are a team of three? You want to be a team of three? Okay, so you guys get the first question, okay? And do you want to time it? Do you have a stopwatch? Let's see how long it takes. Okay, so what is 2 times 2? Okay, second, fraction? 1, okay. Okay, ready? You guys are ready? Okay, so set a high bar. You ready for it? And I'll give a chocolate bar to whichever team wins this, okay? All right, ready? Cosine of 2. It is actually defined. Okay, so anyway, that was kind of an unfair question. You guys can both have chocolate bars. So why did I ask you that? Because basically, the multiplies aren't a big deal, but maybe I can get rid of them, that's good. The cosine is relatively slow, okay? Because for a computer, a cosine is a much harder thing to compute, just like it is for you. This is not exactly a fair question. The way the computer has to work out cosine is actually they have to use like a Taylor series expansion, a whole bunch of multiplications, a whole bunch of summations, and so on. So they use, a Taylor series expansion or expansion similar to that. So much slower. So I'd like to get rid of this. And I'd like to get rid of as much of this as I can. Get it out of my redraw routine to make it as fast as possible. So what can I do? What do you think? So yeah, what do you think? Yeah, so I just compute all this in load map, right? And that actually is going to save me some time. So I don't have to do that. But before I do it, maybe I should measure whether I'm going to teach right after rating week. We're going to talk about profiling. We're going to talk about how to determine if things are fast or slow. So the best way to do things like this is actually to check if it matters. But if it's really easy to speed up, sometimes you just do it, right? Because you go, well, I could code it one way or the other. I'll code it the faster way. So yeah, this code. So let's say I run 200,000 intersections through this for every single redraw. And that, you're gonna see as your map is running, it does a lot of redraws, right? If somebody drags the map around, it's redrawing all the time as it's dragging it around, right? It might do, if your map's fast enough, it might be doing 60 redraws a second. So, and this data is not changing. This is always the same answer for a certain intersection. So we can move it all to load map. So if you get, you may not achieve this, right? But, you know, the point at which people see redraws as pretty smooth is maybe 10 per second, and extremely smooth, you know, something like 60 per second. That's actually not a lot of time, right? Like you're talking about 10 to 100 milliseconds or 16 to 100 milliseconds time to do a redraw. Okay, so it's a good idea to keep your redraw routine pretty light. So how do we reduce computation? We can pre-compute it in load map, exactly what you said. So all I have to do is I change my struct. I already had this global variable intersections, and it used to be storing a position in lat long. Well, I'll just store a position in XY, right? And I'm going to ece2, the actual data type that it defines and uses for drawing rectangles is a two-dimensional point. So I'm actually just going to compute the two-dimensional points for each intersection and store them. And now my routine that actually does the drawing looks a little shorter. It basically just looks up the XY location of an intersection, and it draws, basically there's actually a few different ways you can fill rectangle. You can call it with a point plus a width and a height. So now I'm doing that, okay? So I'm going to draw something 100 meters wide, 100 meters high, with the lower left corner being this XY location that I pre-computed. Okay, so let's take a look at that. I'm going to quickly do a demo. Okay, so the first thing I'm going to do is I'm going to run the same demo I just ran. Okay, so I'm going to run this one again. Okay, so I'm going to show you this, how to do this after reading week, but I put a timer in this program. So this program actually has it's not very much code, but I'm calling a C++ library that allows me to get the runtime of my redraw function. So I want to do this under controlled circumstances. So I'm basically going to zoom in a few times and zoom out a few times so that I can reproduce this after I change the code and know that I'm getting exactly the same thing. So, and it basically is telling me how long it took. So the first, it's pretty fast. It's taking like 8 milliseconds. Okay, so that redraw took it 8 milliseconds, which is pretty fast. I'm going to zoom in again. It takes 7 milliseconds. That one took 2, so there's a bit of bounce. Now it's taking about 6 milliseconds. Okay, maybe 7. Okay, so, and I'm going to zoom out again. And if I want to go right back to my original coordinate system, I hit zoom fit. Okay, so I'll do it again. But it basically starts at about 8 milliseconds, and then it maybe drops down to maybe 6. There's a bit of bounce here. Okay, so if I really want to get, and if I do this, I'm dragging this around, you'll see there's a lot of redraws going on to make that look smooth. Okay, so let's get rid of that. And now I have basically the same program, but I've now changed from storing lat long to storing XY, exactly what I showed you. So I'm just going to make sure that I've got release build. I always want to check speed on release build, so I'm going to build this. Okay, I'm going to run it. Visual Studio is feeling kind right now, so that's good. And let's see, so I'll zoom in again. Okay, so this one starts at about maybe 7 milliseconds and is now going down to maybe 3. So it is faster, okay? The other one was starting at maybe 8 milliseconds going down to about 6, maybe 5 once in a while. So it is faster, but it's not like wildly faster, but it looks like I've maybe cut 30% of the runtime off of this. And now it's no harder to code it this way. So one principle as you're writing milestone2 is if you can compute it in load map, it's better to compute it in load map, within reason. If you're bloating your memory footprint so much that it's painful, then that's maybe not good. But if you go, I'm recomputing this every single time in the redraw function and it's not changing, well, you can move it to load map and that'll speed up your map. Okay, so, actually one other thing I should show you. You might wonder, why did the numbers, let me run it again. Okay, so let's take the first redraw. And as I go in, let's just see this. As I go in, they tend to get faster. So they kind of were about 0.5 or so, or 5 milliseconds, and now they're down to 3. This is because ece2 does what's called pre-clipping. So it very rapidly does quick checks to see, is something you're drawing completely off the screen? If it's completely off the screen, it throws it away. If it is at least partially on the screen, it calls the underlying graphics libraries, which actually these ones are called Cairo and X11. So it calls the low-level rendering libraries to actually draw it. Those libraries take longer, right? Like the work to actually draw all the pixels in a rectangle is quite a bit more than to just figure out the rectangles off the screen. What this means is as you zoom in, it actually does get faster, okay? Because more of your graphics are off screen and ece2 throws it away. It also means one of the optimizations you might think of for milestone 2 is maybe you could check before you call ece2, is this off the screen? There's not a lot of benefit to that because it's the first thing ece2 checks to, okay? So it does what's called pre-clipping for you. Does that make sense? Okay, so let's go back here, make sure I'm recording again. And yeah, this is basically just summarizing. I did some of these measurements offline to make sure that what I was saying would be true, but we got about a 1.5x speed up when the whole map was displayed. And when we're zoomed in and basically there's less actual drawing going on, more just throw things away, it's about a 2x speed up. So yeah, it's worth preloading things. Okay, so that was drawing. We can now draw intersections. You can use these same kind of techniques to actually draw streets and so on, buildings, etc. But we also want to interact with the map. So we want the ability for users to enter things, click on things, enter data. So let's start with mouse clicks. So one of the things you have to do in milestone 2 is a person has to be able to select an intersection by clicking it, okay? And you have to give some information. That's one of the required features. So how do you do that? Well, in graphics programming, you're fundamentally passing control to the graphics system, and then it calls you when it needs something from you. Okay, those are called callback functions. We've already been using one. That redraw function is a callback. Okay, so callback means when something happens, like the screen needs to be redrawn, call this function. How does that work? Well, a function in 243, you guys have probably learned that a function call really means just go to a certain memory address and start executing instructions. So the way a callback is registered is you actually store the function address, okay? So that's how your draw screen was working. What C++ compiler was doing is you gave it the name of a function and you said, use this as the draw screen callback. Whenever ece2 needed a redraw, it basically went to the address in memory where that function exists. That's how we're able to pass callbacks. They're called function pointers, right? It's called a function pointer because it literally is a pointer to the function. Okay, and it allows code that never knew that you existed to call you, right? Because we wrote ece2, and we have no idea what code you guys are going to write. So you've been using it for the screen, but now we're going to use it for mouse clicks. So remember I told you that this is how we pass control to ece2. You set up this application object, and then you call run. And we can pass 4 pointers. Those pointers are actually all function pointers. They're callbacks. And so far we've been using none of them, right? We have used there's another one for the draw screen. We've been using that. Now we're going to use one of them. So 3 of them we're still leaving null. Those are for basically like keyboard input. We still don't want that, so we're not worried about that. But we do now want to know when the user clicks the mouse. So we're going to pass a function pointer into this application.run. And all that means is we're passing the name of a function that ece2 should call when someone clicks in that big drawing area, that canvas where we're drawing the map. We have to write that function. So here's the actual body of it. Okay, so we said it was called act on mouse click, so that's what the name has to be. The signature, like the inputs, the outputs have to match what ece2 expects, otherwise it can't call your function. So in the documentation for ece2 in the header files, it tells you exactly what this is. Also, the example program shows you how to do it. So basically, the first argument is a pointer to the ece2 application that's going to allow you to access ece2 methods. It also passes you a pointer to basically you can get extra information about what just happened. What this is called an event in graphics, like a person clicking the button or hitting the keyboard or moving the mouse, those are all events. So this lets me get more information if I want. And then the most basic information is an X and a Y coordinate of where the person clicked the mouse. I can basically look at this event if I want to see was it left mouse button or right mouse button, that kind of thing, right? Were they holding down shift or not? But for now, I don't care about any of that. All I care about actually is this X and Y. Where did they click? And this X and Y that's passed to you is in your own coordinate system. Okay, so you asked ece297 to use this coordinate system. When it tells you where the mouse is clicked, it's going to tell you it in your own coordinate system. So it's going to be this XY on the surface of the Earth. Okay, so we got a couple printouts. I basically want to figure out what intersection did the person click on. Graphics libraries do not know what's on the screen. Okay, so you draw stuff in that main canvas, it doesn't know what the picture is. It doesn't know these are intersections, etc. It just does what you said, drawing a bunch of rectangles, and immediately forgets it. That's why it has to call you every time it has to be redrawn. It doesn't really know what to do. So similarly, when a mouse is clicked, it can tell you the mouse was clicked here. It knows the pixels. We don't pass you the pixels. We convert it to your own coordinate system and give you that to be more convenient. But now you've got to decide what that means. Right? It has no idea what it means. So how would you find what intersection is closest to this XY that was clicked? So what do you think you have to do? It will fit in this much code. so that's a hint. Okay, do you know where the intersections are? Do you know them in your own coordinate system? Right, like you just loaded this in load map, right? We loaded up what is the XY coordinate of every single intersection. And we said, let's use that coordinate system. We told ece297 that. When the person clicks the mouse, that is the most important information that ece297 is passing back to you. The X and Y are where it's clicked, it's in your own coordinate system. Okay, so you now know where they clicked, and you know where all the intersections are in the same coordinate system. Yeah?
Do we just use like find closest intersection?
Yeah, you can actually call it find closest intersection, right? I think that one was lat long, okay? Yeah, so basically you could say, well, I'll convert the XY back to lat long and call that function, or maybe I'll write another version of it that directly uses XY. Either way will work, okay? So I think here, yeah, we used our helper functions. I said, we'll write these helper functions that convert from XY back to lat long, and now we can use one of our M1 functions, okay? And that M1 function was, I think you probably found not that hard, right? It just kind of looked through all the intersections, seeing what was the closest one. This is the basic technique of what's called hit testing. Right? Like, what did I click on? It is really just go figure out what's closest or what's underneath that. And the graphics library can't do it for you in the part where you're drawing, right? You have to do it. It doesn't really know what you're drawing. Okay, so now I want to highlight that. So I want to actually give some visual feedback to the user. You clicked on this intersection, where is it? So I need to draw it differently. Okay, so here's that function that I just wrote. I figured out what the intersection ID you clicked on was. And what I'm now going to do is I'm going to say, okay, let's get a renderer. So it's nice that it passed me this application pointer because I can actually ask the ece297 application. There's a method in there to say, give me a renderer. I'm going to set my color to be red, and I'm going to draw an intersection. And I'm going to draw it exactly the same way I usually do, right? At its XY location, I'll draw width and height. From that lower left corner to 100 meters to the right, 100 meters up, draw a rectangle. But it'll be red, so it should show up. Okay, so let me show you what that looks like. Oops, let's go there. Okay, so let's get rid of this. Okay, build this, run this. Okay, so here's my graphics. I'm going to zoom in a bit so it's a little easier to see things. Let's make this a little bigger. Okay, so I'm going to click on one of these intersections, maybe this one. Okay, and it turned red. Does everybody see it's red, or should I zoom in more? Okay, I'm going to zoom in so you can see it better. And it's kind of gone. Okay, let's move it right in the middle of the screen. So let's click on it again. So it's red. If If I zoom in and it's not, it's gone. Okay, what's happening here? Let's do it one more time. Maybe it's just bad luck. So maybe I'll click on this one. All right. And then I'll zoom out. And it's gone again. Okay. So I'll click, go back to this guy, zoom in, it's gone again. What's happening? Yeah. Yeah, the redraw is overwriting it. Okay, so I managed to highlight it, but only for one screenful. As soon as the person interacts with the graphics and there's a redraw, I lose it. So it's transient. Do you think this is good? So we've actually had students, TAs are told to watch for this too. Okay, so don't do this because they will check for it. We had actually a few students who've argued this is a design feature. There's no program in the world that does this. If you're typing in Word and it doesn't redraw, it doesn't throw your text away, right? So you can't argue this is a design feature. This is not a design feature. So how are we going to fix this? Okay, so we know what the problem is, but what are we going to do to fix it? What do you think? So with graphics, you have to get used to this notion of callbacks. That you're not fully in control. You're basically setting things up. You're making functions that will be called at certain times, but you're not really in control of when they get called. So when the mouse was clicked, we got called. We could highlight something, but after that, our redraw function gets called, and we can't put like something else in between. So the only thing we can change is our redraw function. Right? Our redraw function has to do the right thing, and right now it's not doing the right thing. It's overwriting or highlighting. So what do we have to do? At a high level, what do you think? Let me bring up the slides. Any ideas at all? How can we make our redraw function draw that in red? So that's what I want. No ideas? So we need to have some state, right? We need to store that this thing is highlighted because it might get redrawn 300 times. We have no idea. Every single redraw needs to know this thing is highlighted. Okay, so what we need to do is what's called stateful graphics. Okay, we can't just, in a callback when the person clicks the mouse, we can't just draw something and forget about it. We need to remember that the person highlighted this. So we want to highlight an intersection from when it's clicked. And there are basically three things we're going to do. We have to register our callback function, and we already did that, right? We wrote a function and we passed it into that application.run. So we set up the callback for mouse clicks. We have to write the callback function, okay? And we already did that. We found the intersection was closest to the click. We drew it, but we don't want to do that anymore. What we want to do instead is we want to store that it's highlighted, okay? And then our screen redraw function has to be changed to actually pay attention to this highlighting. Once we do that, it'll highlight every single time. Okay, so we've already hooked up the callback, right? In the EasyGL documentation, it says this is the second function parameter is the one that gets called when the mouse is clicked. Let's see. In general, the four callbacks are this. There's one that gets called right after the window is set up, one that's called every time the person clicks the mouse in that main canvas where you're drawing, one that gets called when the mouse is moved in that area, and one that gets called when the person hits a keyboard key and the mouse is in that area, okay? So there are four callbacks you can set up. Look at the example program that shows you how you can use all of them. And if you find some of them you don't need to use, that's fine, but they all exist. Okay, so we already did this. We found the closest intersection. What we need to do is we have this intersection data already. So we have this vector where we have a bit of data for every single intersection. We're going to add a new variable inside that structure. Highlight. It'll be a Boolean, and we'll default it to false. Okay? So when this vector is first constructed, nothing is highlighted. But in our mouse click routine, after we figure out which intersection you clicked on, we're going to basically set its highlight flag to true. Does that make sense? Okay, so we're not redrawing it, we're setting the highlight flag to true. Okay, and then our drawing function now needs to be a little bit more clever. So this is the redraw function that we've been using. And what we've changed is it's now checking for every intersection, is the highlight flag set? If it is, it's going to set the color to red, and if it's not, it's going to set it to black like it has been before. Does that make sense? Okay. Okay, so let me do a quick demo of that. Okay, so let me zoom in a few times so this looks a bit bigger. Let's see. So let's find an interesting spot where I can see some intersections. Okay, so I'm over top of this intersection. I'm going to click on it, and nothing happened. Okay, I'll try it again on the one next to it. Nothing happened. So it seems like a fail. But then when I zoom in, they're both highlighted. Okay, so I'm going to click on this one next to it. Nothing happens, but I'll zoom in again, and now another one's highlighted. Okay, and so on. So let's zoom in again. All right, now I clicked on it. So what's happening? Now let's zoom out and let's see if this highlighting stays. Okay, I mean, I'm redrawing a whole bunch of times. Seems okay. What? So it kind of works, right? Like it does actually stay highlighted now, but it has this annoying behavior. If I click on something, I'm about to click, I clicked, nothing happened. But now if I just move the screen a little bit, it shows up. Why? Yeah, what do you think? Yeah, so I'm missing this redraw function. Well, I'm waiting for the first redraw, and things only get redrawn when the user does something, right? There's some reason to redraw. So it's kind of annoying. So the fix for this is relatively simple though. Okay, let me make this, hide these again. So basically there's a function in ece2. It's a method of the application. So we passed in this application pointer, or it automatically got passed in. So that's the whole ece2 application. There's a function called redraw, refresh drawing, and that forces a redraw. So after this intersection, you just click the mouse, I've highlighted the intersection, I know the graphics are stale, I want to force a redraw. So I just force one right now. And now it'll show up right away. Another thing I'm showing here is basically, this is just code to take the intersection name and put it in a string stream, okay? Which you may remember from 244. It's just basically a class that C++ has that allows you to kind of treat strings as streams. And I'm going to take that string stream. I can take the actual string in and out with the stir method. And I'm passing that to another function that ece2 has called update message. Okay? There's a little message area at the screen bottom in the default UI layout we give you. So this call, you can just display one message there if you want. So I'm going to basically show the name of the intersection there, and I'm going to force the intersection to be redrawn, or the screen to be redrawn right away. So let me go out and show that. Okay, so let's hit proceed. That will go back to my, get rid of that application.run, go back to my code. All right, I'm going to build this again. I'm going to run it. Okay, let's see if this works better. So now if I click on this, it shows up right away. Click on other things, it shows up right away, and it stays there as I do redraws. Okay, so it's all fixed now. Okay, and I don't think I showed you the status bar, but his name was showing up in the bottom too, so I didn't really highlight that. There's one last issue, okay? Because I didn't show you this, but the selection is actually not very accurate, okay? So if I go in and I show you where I click, you're gonna find that I sometimes kind of get the intersection that's next to me, okay? And the reason for that is that I'm drawing the intersections from like where they actually are, and then 100 units to the right and 100 units up. So I'm not centering my rectangle on the intersection. So what that means is I am finding the closest intersection to where I click, but visually I'm not drawing the box centered around it. I'm drawing it kind of starting there and going up and to the right. That offset is annoying, right? Like it means that when a person is clicking on where you visually show the intersection, they think it's at the center of that box, but it's actually at the lower left corner. So that's bad because it makes it hard to click on. And if instead of that, we basically draw the intersections, all I have to do is basically, I basically just have to shift by width over 2 and height over 2 where I start drawing the rectangle, and now it'll be centered, and it's going to be much easier to click on. Does that make sense? So I think in the interest of time, I'm not going to show you that, but that will fix that. Okay, so you guys have two options. We can stop here, or I can show you for another 5 or 6 minutes, maybe 7 or 8, how to add buttons. What would you like to do? Are there people waiting to come in here or not? So, what would you like? I can try to go through this really fast and then have the slides after, or I can leave it till after reading it. What's your preference? Okay, we'll try it. If you need to leave, go ahead. Okay, so everything I've shown you so far is how to draw in that main graphics area. But you're going to wind up having to add some what are called widgets, things that people can interact with, buttons and so on. So the simplest thing you can add is a button that you can click on, and when you click on it, it calls some callback, which will do whatever you want. I'm going to make a simple button called Pinkify, which is going to draw a pink background, okay? In order to make a button like this, I need to basically create the button, and ece297 has a call to create a button in that menu area. When do I create it? I create it when the window's first created. Okay, I want it to be there all the time. That's why this initial setup routine is useful. So I can basically say, call this initial setup function, and in there I'm going to make some more buttons and stuff. Okay, so I'm going to use my initial setup callback. After I've told ece297 what my initial setup is, I have to actually write some code in that initial setup routine. It's going to make the button, and it's going to connect a callback to it, like what happens when you click on it. And my callback is just going to store, have you turned the screen pink or not? Okay, and then my redraw function is going to pay attention to that. So that's the steps I'm going to follow to do this. I have to think in terms of callbacks, right? I'm kind of registering what happens when various things happen. So I set up my callbacks. So basically I'm passing in one more thing to application run, this initial setup routine. That initial setup routine, I'm calling a function called create button that ece297 provides. I give it a name. I say which row I want it to be in that menu area. And I give it the name of a function that should be called whenever it's clicked on. And then I have to actually write that function. Okay, so the function I want called is called toggle pink. It must match this signature. Okay, so signature is defined in ece297. It takes a pointer to essentially the UI element. I don't actually need that, so I'm just going to comment it out so I don't get a warning. I'm going to comment out the name of the variable to tell the compiler I'm intentionally not using that. I don't care, but I must leave it there. I can't just delete the parameter because I must match the signature. And I've also passed the application pointer for ece297 so I can call things. I want that. So I'm going to basically give that a name. And all I do is I have a global variable called Pinkify, and I just toggle it. If it was true, I make it false. If it was false, I make it true. And then I say refresh the drawing. I want to immediately show what happened. You call the screen redraw function. In my screen, so here I'm showing I've got this global variable, so I can remember if it should be pink or not. And then in my redraw function, I basically check, is this Pinkify set? If it is, I basically want to color the whole background pink. I can actually make this call to say how much of the world coordinate system is visible. So I can actually ask for a rectangle that is the whole canvas that's visible. And then I basically set my color to pink, that's red, green, blue. And then I say fill a rectangle. And that rectangle will now fill the whole kind of visualization area. And then after that, okay, I want that to be the background, so I draw it first. And then I draw all my intersections and stuff on top of it. Okay, so, and that will be it. So let me see if I can do this last demo really fast before the other class overwhelms me. So you'll be amazed by my Pinkify button. Let's see. Okay, so let me build that and run it. Okay, so here's my new, I click my Pinkify button and the screen turns pink, right? I click it again, screen turns not pink, and so on. My highlighting still works. So I've now added it, so it's not a lot of code, right? That code basically made this new button, hooked it up, and now it does stuff. So that's kind of the simplest way to get extra controls in your user interface. And after the first tutorial, after Reading Week, we're going to teach you how to make some additional UI elements if you want. But most of what you're doing in Milestone 2 is really not about creating UI widgets, it's about visualizing. Okay, so you have what you need to do the bulk of Milestone 2 at this point. Actually, you can do it all if you want, because you don't have to make any other UI widgets beyond what we just talked about. But when we come back, that first tutorial, we'll talk about how to make more UI widgets, how to change the UI layout if you want, and also how to show you what I did in terms of timers. We're going to show you how to figure out what's fast and slow. Because in Milestone 2, it's also good to make your code fast. Okay, that's it. Have a great reading week. Thanks.